So we have two learning targets for today. All right, we're going to use, and then these little things ought to look sort of familiar. That means angle-angle similarity, postulate in this case, side-side-side similarity theorem, side-angle-side similarity theorem. So the little similar sign behind the letters indicates that it's a similarity theorem instead of a congruence theorem. So that means when you use it, you got to put the similar sign after, don't you? Otherwise, you'll end up saying something that you don't mean to say. Okay? So we're going to use those, and then we're going to solve some problems. Similar triangles are actually fairly useful things outside of a classroom. All right? And I'll show you a problem that we're going to do some indirect measurement, and it works out kind of neat. So our definition of similar polygons is that they're two polygons. Our informal definition, same shape, different size. Our formal definition is that all pairs of corresponding angles are congruent and all pairs of corresponding sides are proportional. But especially if there's a lot of sides, that gets really, really hard to deal with. And even with triangles, to use the definition, you'd have to show that all three pairs of corresponding angles are congruent and that the ratios you make from all three pairs of corresponding sides are all proportional. Kind of like we did with our congruence theorems, we can cut the work down. Okay? So our first one is the angle-angle similarity postulate on page 474, and it says this: if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. All right? So you don't have to know anything about any of the sides. Now, it's angle-angle, but remember that we have something a while back called the third angles theorem that said if two angles of one triangle are congruent to two angles of another triangle, then the third angles are also congruent. So if you know that two pairs of corresponding angles are congruent, don't you in fact know that the third pair of corresponding angles are also congruent? And that guarantees that they have the same shape. Okay? If all three angles match up to all three angles, that guarantees they have the same shape. Make sense? All right. Let's see if it does. So we're on page 479. And it says, determine whether the triangles are similar. If so, write a similarity statement. And then explain. And if the answer is yes, our explanation can just be one of these three methods. Of course, we only know one of them so far, so there's a little hint. So let's see if we can make angle-angle similarity postulate work here. All right, so when I look at this, I do see two triangles, right? I also see two parallel lines and a couple of transversals. One thing I see is that vertical angles are congruent, so there's one pair of corresponding angles that are congruent. And then, look at the screen. Whenever you have two parallel lines and a transversal, don't we know that all angles are congruent? So there's another pair of corresponding angles congruent. And in fact, couldn't I have used that transversal and get a different pair? So depending upon how I want to go about this, I can get at least two pairs of congruent angles, can't I? In fact, getting three is not difficult. Two is all I need. So I will say, yes, they are similar. They want us to write a similarity statement. So I'm going to call the triangle XYZ is similar to triangle. And then just like we did when we were dealing with congruent triangles, we must match up the corresponding angles. So I wrote X first. Now, because of our alternate interior angles theorem, X would be congruent to W, right? Isn't that the way I had it when I had the transversal drawn in and all? And then what's Y congruent to? V. And then the angle Z on the left is congruent to the angle Z on the right. So my similarity statement is triangle XYZ is similar to triangle WVX. That doesn't look like a WVX, does it? WVX. There. Now we have to explain. Our explanation is angle, angle, similarity, and it's postulate, but if you put angle, angle, similarity, we're good. Not so bad, right? Now let's take a look at our next method, the side-side-side similarity theorem. This is on page 475. And then on this one, on angle-angle similarity, we didn't need sides. On side-side-side similarity, we don't need angles. But it's not corresponding sides congruent, is it? That's not what similar figures have. It's corresponding sides proportional. So the theorem says this. It says, if the corresponding side lengths of two triangles are proportional, that means you make a ratio from all three pairs of corresponding sides, and all three ratios are equal to each other. Okay? Now, you may have to reduce them to make them equal, but they're all equal to each other. Then, the triangles are similar. Okay? So, for instance, and I'll make up some lengths that this won't be to scale at all, but if I have like 8, 4, 6, 3, and 4, 2. I can use the side-side-side similarity theorem to show that those triangles are similar, because 8 to 4 and 6 to 3 and 4 to 2 are all equal, aren't they? Because they all reduce to 2 to 1. So that's proportional. That's what we mean by proportional. All right, we think we're okay with side-side-side similarity? All right, then side-angle-side similarity. Now, again, remember, it's not going to be sides congruent, proportional. So this theorem says, if the lengths of two sides of one triangle are proportional to the lengths of two corresponding sides of another triangle. So the side, the S in the front and the S in the back are from corresponding sides that are proportional, not congruent. Now, they can be congruent, in which case the ratios would be 1 to 1, but proportional. And the included angles are congruent. So that means this. Look over here at the figure. That this side and this side make a ratio. This one and this one make a ratio, and those two ratios are equal. That's what the sides being proportional means. And then the included angles are congruent. So angle S has to be congruent to angle Y. Then the triangles are similar. So this method's a little more complicated. Okay? You have to have two pairs of corresponding sides proportional and the included angles congruent. Two pairs of corresponding sides proportional, the included angles congruent. That's 479. So we're still trying to decide whether or not the triangles are similar, or we write a similarity statement, and then we explain. So number 2 here. It's a little bit of a trick, because they give us two sides for this one, and that at right angles included, and they give us two sides for this one, but that's not the right angle. So as it is, we can't do side angle side similarity, can we? Okay? So let's think for a minute. Look at the triangle ABC. It's a right triangle. If one leg's 3 and one leg's 4, can I figure out the hypotenuse? Yeah. Anybody remember what the hypotenuse turns out to be? 5. It's a 3, 4, 5 Pythagorean triple. If you don't remember that, it's okay. 3 squared plus 4 squared equals c squared. 9 plus 16, 25. Take the square root. 5. So we get 5. Okay? Now, If I have over here one leg 6, the hypotenuse 10, can I figure out that other leg? Yeah, what's it turn out to be? 8. It's a 6, 8, 10 Pythagorean triple. If you don't know that, it's okay. You can figure it out. 6 squared plus b squared equals 10 squared. 36 plus b squared equals 100. B squared equals 64. Take square root. B equals 8. So now that we know that, now let's try again to see whether or not we can say these are similar triangles. So I can try side, side, side. And remember, there's no big trick. Just the shortest side has to correspond to the shortest side. So the shortest side of 3 corresponds to the side of the other one, 6. Next shortest side, 4, corresponds to the next shortest side, 8. Longest side, 5, corresponds to the longest side of the other one, 10. Are those 3 ratios equal to each other? Yes, because they all reduce to 1/2 or 1 to 2, don't they? Okay? So we can say yes, and we can say side, side, side similarity. Could I also say side angle side similarity? I actually could. I could pick out the 3 to 6 and the 4 to 8, they're equal. So here to here, here to here. And then the included angles are right angles, so they're congruent, aren't they? So I could actually use 2 different methods. Do I need to use 2 different methods? No. I'm going to stick with side, 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 because that's what I happen to see first. But I'm letting you know, if you saw side angle side similarity, you're correct as well. Okay? So, what do we say over here? We say yes. I'll skip the similarity statement for a minute. The reason is side, side, side similarity theorem. But I need to put in the similarity statement. So if I call the one on the left, triangle ABC, is similar to, now, AB is going from the right angle down the shortest side. So I need to start over here at the right angle and go where? To E or to D? To D, down the shortest side. You follow my reasoning? So I go to D, that must mean E comes last. All right. Any questions on number 2? Number 3. Now they've given us all 6 side lengths. So we need to try side, side, side similarity, don't we? That's what we need to try. So let's see. The shortest one on the left is 6. The shortest one on the right is 4, so they have to correspond. The next shortest one on the left is 8. The next shortest one on the right is 5, so they correspond. The longest one on the left is 12. The longest one on the right is 8, so they correspond. Are those 3 ratios equal to each other? Not, are they? 6 to 4 can reduce to 3 to 2. 8 to 5 doesn't reduce, does it? So they're not equal, so already we know the answer is no. And then if you want to go ahead, 3 to 2, what's that reduce? Or 3 to 2. 12 to 8, what's that reduced to? Divide a 4 out. All right, it is a 3 to 2, isn't it? But not all 3 pairs of corresponding sides equal the same ratio. So we have to say no. So there's no similarity statement to write, but we do need to explain. No, and I'll just say corresponding sides are not proportional. Make sense? All right, do number 4. Did you get what I got? Any questions? Were you able to? Now, you could write a different similarity statement than me, couldn't you? And it still can be correct as long as J corresponds to S, K corresponds to Q, and L corresponds to R. Okay? All right. Let's try number 5 here. It says in the figure, segment AB intersects segment DE at point C. Well, we can see that in the figure. Which additional information would be enough to prove that triangle ADC is similar to triangle BEC? It says additional information. That must mean they think we have some information as it is. And we do. We know that, don't we? Because vertical angles are congruent. They don't tell us anything about side lengths. They don't tell us anything about any other angles, do they? So let's just go through one at a time and see if which one of these letters gives us enough information to use one of our methods. All right? So let's try A. Angle DAC, DAC is this one, and angle ECB, that's this one, are congruent. That's not helpful. That's just confusing. So now we have two angles from one triangle congruent to one from the other. No, that's nothing. All right, so let's get rid of that. So it's not that one. Segment AC and segment BC are congruent. There's segment AC, there's segment BC. So they're trying to take us to the side angle side similarity, aren't they? We've got side angle. That's as far as it goes, isn't it? Okay, because that ratio would be 1 to 1, so that's fine, but we got nothing else. So it's not B, C. Segment AB, nope, segment AD and segment EB are parallel. Oh, that's really helpful. Two parallel lines cut by transversal. That pair of alternate interior angles would be congruent, wouldn't they? Is that enough to prove that the two triangles are similar? Yep, by angle-angle similarity. So the answer is C. I don't even need to try D. I found one that worked. So far, so good? Now, reflexive, symmetric, and transitive properties all work for similarity, like you might guess if you stop and think about it. Okay? Triangle ABC is similar to itself. And by the way, the scale factor would be 1 to 1. Okay? Because the ratios would all be, reduced to 1, wouldn't they? Like 5 to 5, 6 to 6, all become 1 to 1. All right? It's also symmetric. If triangle ABC is similar to triangle DEF, then triangle DEF is similar to triangle ABC. And transitive. If triangle 1 is similar to triangle 2, and triangle 2 is similar to triangle 3, then triangle 1 is similar to triangle 3. Okay? So here then, at the bottom of page 478, is a summary of our three methods. Angle-angle similarity postulate, side-side-side similarity theorem, side-angle side similarity theorem. If you get confused and you don't remember what works and what doesn't, then look at the bottom of page 478 at that little summary. All right? Now, we've identified them. We've written out similarity statements. We've used our methods. Let's see if we can solve some problems. So number 6, identify the similar triangles and then find each measure. Now, finding lengths of sides is a really, really common way to use similar triangles, okay? So let's see what we've got going on here. We're supposed to find the length of KL, which they conveniently called X for us. So we got to solve for X. That's what we need to do. Now, it says identify similar triangles. These two triangles are similar. These two triangles are similar by angle-angle similarity, aren't they? So if I call the triangle on the left, I go X, Y, Z, is similar to triangle. What's angle X congruent to? J. What's angle Y congruent to K? And then angle Z must be congruent to angle L. All right, so we've identified the similar triangles. Now find the measure. Okay. By looking at our similarity statement, I see that side XY with a length of 5 corresponds to side JK with a length of 4. Since these triangles are similar, every pair of corresponding sides has the same ratio, doesn't it? All the ratios are equal. So any ratio I make from another pair of sides must equal 5 to 4. In other words, 5 to 4 is our scale factor, isn't it? All right, so let's make a ratio of another pair of corresponding sides. YZ, 15, corresponds to KL, X. Now we can solve this. Okay, those ratios have to be equal. Now I'm going to end up using cross products, but even before I do that, do you know the answer? It's 12. You don't really have to do cross products. You're writing equivalent fractions, right? We know these fractions are equal. If I took the one on the left and just multiplied it by 3 over 3, isn't that a way to get equivalent fractions? Sometimes you reduce to get equivalent fractions. Sometimes you multiply to get equivalent fractions. Wouldn't that turn into 15 over 12? I'm going to get 12, but that's okay. So 5x equals 60 using cross products. X equals 12. So the length of KL is 12. Does that make sense? Do you see how identifying the similar triangles can be helpful? If the drawings, if it's hard to tell from just looking what side corresponds to what side, writing it out as a similarity statement makes it easier to pick. All right, number 7. They want us to find the length of VS, which, again, they called X for us. So that's helpful. Now, we've got 2 triangles here. Look at the screen. We've got the little red one and the big blue one. Are those triangles similar to each other? Yes, because of angle-angle similarity again. There's a pair of right angles. They're congruent. Angle S in the red triangle and angle S in the blue triangle are the same angle. So they're congruent to each other. So by angle-angle similarity, these triangles are congruent. So if I call the blue one triangle QVS is similar to triangle, then what do I need to call the smaller one? What corresponds to Q up here? R over here. V is a right angle. T is a right angle. S better be congruent to itself. So does that similarity statement make sense to you? Now, let me get rid of all this over here so we can see it better. This side of 5 corresponds to this side of, oops, let me change colors, to this side of 3. How do I know? Look right here. QV corresponds to RT. So the length of QV to the length of RT is our scale factor. Now, look at another pair of corresponding sides. VS corresponds to TS, doesn't it? What's the length of VS? Well, now, what is it right now before we solve it? X. And what's the length of TS? Everybody see what I've done? And we're going to get 20, right? 3 times 4 to get the 12, so 5 times 4, the numerator's got to be 20. Or use cross products. So the length of VS equals 20. And by the way, I'm fine with you figuring it out without using cross products. not all of them can be figured out. I mean, you get decimals and fractions and stuff, and that can get a little complicated. But when the numbers work out kind of nice, and you can just figure it out by thinking about equivalent fractions, that's good. That's good math. Okay? All right. And I promised you one where you could actually take similar triangles outside of the classroom and use them. Number 8. A cell phone tower casts a 100-foot shadow. Let's draw that. So, there's the tower. So draw this on your paper. You need the drawing on this one. There's the tower. They don't tell us how tall it is, so I call it T for tower. You can call it whatever you want. I'm calling it T for tower. It casts a 100-foot shadow. That means if you go along the ground 100 feet, you come to the end of the shadow. So 100 feet. Now, we've got to do a little assuming. Hopefully, the tower is vertical. If it is, it'll make a right angle with the ground. And again, if it's on the side of a hill, we really can't do this, can we? It needs to be on pretty flat ground so that the tower and the ground make a right angle. All right, let's keep reading. At the same time, a 4-foot, 6-inch post near the tower casts a shadow of 3 feet 4 inches. So here's the post. It's 4.5 feet, right? 4 feet 6 inches, 6 inches, half a foot, 4.5 feet. The shadow is 3 feet 4 inches. Now 4 inches. Don't make a mistake and put like 0.4. 4 inches is 4/12 of a foot. It's 1/3 of a foot. Right there. Everybody understand the drawings? Now, here's what happens, okay? The post has to be near the tower because the sun, here's Mr. Sun, hits the top of the tower, casts the shadow. So if I draw an imaginary line from the top of the tower to the end of the shadow, I get a triangle. Do the same thing from the top of the post to the end of the shadow, get a triangle. If the tower is in Murray and the post is in Omaha, this won't work because the sun's not hitting them at the same angle, okay? But if they're in the same field, this works fine. Now, you're just going to have to trust me on this. The angle that the sun makes right here from the imaginary line and the tower, and the angle the sun makes right there between the imaginary line and the post, those angles are congruent. So by angle-angle similarity, we have similar triangles. Since we have similar triangles, that means if we make ratios out of corresponding sides, those ratios are equal. So, T, the height of the tower, to 4.5, the height of the post, because they would be corresponding sides, wouldn't they? Equals 100, the length of the shadow, to, and I did not call it 3.333. You can, you're going to get the wrong answer, just barely, to 3 1/3. You understand the ratio? All right. Do cross products. I get 3 1/3 T equals 450. 3 1/3, that's very inconvenient to divide by. So I changed it to 10/3, which is actually easy to divide by. To divide by a fraction, don't you just multiply by the reciprocal? That way all that divides out. So you get T on the left, and you get 135 on the right. Let me show you how I got to 135. I divided that 10 into the 450 and got 45, and then 45 times 3 is 135. So that means the tower is 135 feet high. which is kind of, hey, that's a lot easier than sending Adam to climb up the tower with a tape measure. Okay? And here is the assignment. Page 479, 1 through 8, 9 through 23 odd, then back up and throw 22 in there, 29, 32, 43 through 45.